Hi, everybody. Yeah, I'm here to talk about something very exciting. It's not just ordinary programming; it's meta-programming. Meta-programming is really great because it's all about getting the compiler to write code for you. So meta-programming is all about writing programs that write programs. That's pretty exciting stuff, right? It means we don't have to program anymore. We can all retire. Um, What it means in Scala terms is giving the compiler information to help it generate code. Write code so you don't have to, or augment your code so that you don't have to modify that. And there's a number of situations where metaprogramming is really useful. I'm going to talk about two. I'm going to talk about building nice syntax for things, like domain-specific languages. I'm going to talk about getting rid of boilerplate, so eliminating mechanical repetitive code from your code bases. And the reason I'm giving this talk is that there are various different approaches to metaprogramming that people like to use, and I want to provide some kind of insight into when they're useful, because in addition to being about writing code that writes code, metaprogramming can also be a bit difficult to get right. And we can spend some time going down one route and then deciding it's not the right route and going down another route. So we're going to look at two different ways of doing metaprogramming. We're going to look at macros. We're going to look at Shapeless. Spoilers, the answer is that both of them are applicable to different situations. I'm not going to pick one over the other. And we're going to look at basically the decision you have to make as to which approach to use given a problem, right? We're going to look at that. We're going to look at how to tie your metaprogramming into your normal programming in a way that makes it easy to do the metaprogramming. We're going to look at some gotchas, and we're going to do it through looking at some cool examples. So I have two examples in this code, warning in this talk. Sorry, a warning that I'm not actually going to talk about much code directly. If you want to see all the code I'm talking about, go to that GitHub link now and start looking at the code there. I'll give you just a high-level overview, but you can always browse through it on your laptops. Okay, ready? Ready? Okay, great. So we've got two examples. The first example is the simplest possible thing I could think of, which is constructing values. Okay, so the use case here is we have a case class. This ice cream case class I tend to be using a lot these days. And we want to be able to create instances of ice cream but without actually doing any work ourselves. So we don't want to have to specify the constructor arguments. We just simply want to say, create an ice cream and have the compiler produce the value for us. Okay, so let's look at how we can do this with macros and with Shapeless. With macros, the idea is we are literally going to allow the compiler to rewrite our code so that whenever we write this, it expands it to the right constructor call, and that's the resulting code that's run. Okay, and to give you the very high-level overview, we do this by defining create as being a macro. So this is, a regular method definition. I'm going to create a value of type A. I'm going to return an A, but we implement it in terms of another method, which is a macro. And whereas create is something that deals in types and values, a macro is something that deals in the type metadata that the compiler stores, and it generates expressions for us. So the code for the macro sort of looks like this. We start off with a type, we can get some metadata about that type, and we return this thing called a tree, which is an expression, right? So it's like an AST tree. So we're basically going to find the apply method, call it with the right parameters, and we're done. So let's think about how we would do that. And you can kind of think about how you would write this macro without knowing anything about the macro API, the Scala Reflect API that we can use in Scala at the moment. We'd start off with our type ice cream, and then we would look up information about that type from the compiler, right? That could be any kind of type, but we're hoping it's a class, because the next thing we're going to do is we're going to go look at the class definition. So we find what's known as a symbol in the macro API, which basically is the code you've used to define that thing. And you can look at the symbol and find out what the name of the type is, what its supertype is, what all of its methods are, and you can jump to the companion object. There's a symbol for that. Then we can look at all the methods in the companion object. We can literally find a method called apply, right? Look for a method with that right name, the right return type. We look at all its parameters. and then we generate default values for those parameters. This is how our macro can work. Okay? This is the code for that macro. I said I wasn't going to go into detail, but it's all there. Length of code is not necessarily an indicator of quality of code, but it's 40 lines for what little value little that's worth. And you can kind of see just from the zoomed out version, this is that initial macro that I showed you, but with the sort of bits filled in there. This is a helper for finding a method called apply, and this is a helper for mapping from the types of each argument to the values you want to put in. So I'll say I'm not going to go into detail about the whole thing, but I am going to look at this last method in a little bit more detail because it ties in to a larger point about how we integrate metaprogramming with our normal code. So this is the simplest possible implementation I could find for this method. Remember, it's called a create apply param, and remember we're looking at the type of one of the parameters to our apply, and we're trying to work out what to fill in for the value for that parameter. So if it's a string, we fill in an empty string. If it's an int, we fill in a 0, and if it's a boolean, we fill in a false. And if we don't know what type it is, we just ask the compiler to fail with a helpful error message. Fail. Okay. All right, so this is really basic, right? But it does give us what we need. Ice cream there has a string, an int, and a boolean. So, okay, all right. Ice cream gives us a string, an int, and a boolean, and the compiler can rewrite that into our constructor call. Okay. But there are a number of problems with this approach. Can anyone suggest a problem with this approach? Say again? What if we have several apply methods? That's an interesting one. That's a really good valid point. What's another problem? Miles? There are other subtypes of string. Okay, all right, we might touch on that a bit later. Yes, all right, that's a weird one that I hadn't thought of, so unsurprisingly. Anyone else? What if the user has defined their own data types and their ice cream has like a currency value or something they've defined? This doesn't work for it, right? And it could never work for all types. I can go back and I can modify the definition to do doubles and booleans, but I can't, do prices like Eric showed earlier. Like that's a user type. So we have at least two problems there, and I want to focus on these problems because we're going to solve these and try and make this library much more general, and we're going to do it without doing any metaprogramming. What we need is we're going to go back and we're going to rewrite our macro, and we need a mechanism for looking up bits of functionality by type. So I want the user to be able to program rules to say, when you see this type, here's the value I want you to generate. Now, can anyone think of a mechanism to do that in Scala? Go on. Really? Nobody? What if you wanted to define JSON serialization for different types? Look up a type and find out how to serialize it to JSON. What pattern would you use? A type class, exactly. This is what we're looking for. So I'm going to make a type class. I've called it pure because there's a method in cats which sort of does the same thing. But aside from the fancy name, it's just a trait with a type on it, and it has a single method called value, which will give us an instance of that type. And then we can define it for the 3 types we care about, the 4 types we care about. The user can define instances for their types, and so it's customizable and extendable. Okay, now I've marked all these as implicit, which means I can get hold of them via implicit parameters, and I can also do this thing here. If you've used implicitly before, you can say implicitly, find me something that's marked implicit of this type, and it will go, okay, here's something, it's that type, it's marked implicit, and it will return it. So I can now use pure to fill in the values of those parameters. So I'm going to rewrite my helper method, create apply param, and okay, it sort of looks a bit complicated. That code actually just says implicitly pure of the param type. So we summon the pure and then we call its value method. The reason we got all this underscore root underscore stuff in here, one of the gotchas with Scala macros is that they are unhygienic, which means the meanings of any identifiers I use in the macro, they are whatever the identifier means at the call site. So if somebody redefines predef or implicitly at the call site, my macro can end up meaning something else. So to get around that, I've just globally referenced these objects. Okay, so this now allows us to do it gives us much more flexibility about our solution. So we can write something like create ice cream. It expands to this lovely piece of code. But the key thing is the result here is an empty string, the result here is a 0, and the result here is a false. And so we have an extendable solution. So we've built in user customizability and the ability to handle any parameter type, not through using metaprogramming, but through using regular old Scala type classes. And regular old Scala type classes are super powerful, and we shouldn't forget about them just because we have new toys like macros and Shapeless. So the only remaining problem with macros is they're brittle in various ways. Someone here said multiple apply methods. I can't remember who it was, but you're absolutely right. There are various ways which our macro can fail. Some of these steps here, these red steps, can fail. So what if we call create with a type that's not a class? We won't be able to look up a symbol. What if it doesn't have a companion object? What if there are multiple apply methods? All these different things, where there are all these little details about how the user has written their code that we have to be able to deal with and gracefully either fail or do the right thing with. And so there's too much, I would say, for this kind of problem, we have to deal with too many problems with a macro. So let's have a look at how we would solve that with Shapeless. Okay? So we're actually going to go back to our pure type class here, but we're going to reuse pure not to summon all the parameters to put into our constructor. We're going to use pure to summon the entire thing. We say, I want a pure of ice cream, and then that pure of ice cream will generate me an ice cream. And the way we're going to do that is we're going to define a new type of pure that works for any parameter type here. Now, I'm not going to show you any code for this at all, but I'll show you how it works, and you can see the code in your code bases. So Shapeless will give us this thing called a generic. And a generic is a type class which will map something like ice cream, a case class or an algebraic data type, onto some other type, which kind of tells us what types of field we have in what order. So it kind of files off all the names. We don't know about ice cream, we don't know about cherries or in cone or anything, but we do know string, int, boolean. Those are the components. And then because this type here is traversable, because it's got structure, we can write an algorithm that searches for an instance of ice cream, searches for an instance of pure of ice cream by searching for instances of pure of the different parts of the type. So we start by looking for ice cream, and then we can ask Shapeless, what's the sort of generic representation of ice cream? Okay, it's this H-list, this thing with structure. So if I can generate an instance of that, I can turn it into an ice cream. Okay, well I can generate an instance of that by generating the instance of the string and of the tail. I can generate an instance of the tail by doing that, and I can go all the way down the data structure. So if I can solve H-nil, boolean, int, and string, generate instances of all those things, I can combine them together and create an ice cream. And this is the code. Oh, I lied when I said I wasn't going to show you the code. There's an instance of pure for an empty H-list, an instance of pure for an H-list with a head and a tail, and an instance that says, well, I'll give you a pure for any type A, provided Shapeless can tell me what H-list it has, and I can get a pure for that. So there's a bunch of details in here, which we're going to skip over. There's other talks which I'll reference at the end where we can dive into the details. But in about half the code, we've solved the same problem. And because so the code's shorter, and because this is because Shapeless is working on a different level. Macros are syntactic, right? They're dealing with the nitty-gritty of like what code we've written and what definitions we've made. Shapeless is simply saying, what's the structure of this type? Okay, it's these three things. All right, well, I'll summon instances for these three things and combine them. It's a much higher level mechanism to solve quite a high-level problem. Now, what about the elephants in the room? Everyone always asks about the error messages and compile times. Well, error messages with Shapeless, well, there's really one, could not find implicit. it's not the most helpful error message. Apparently, it's going to get fixed in DOSI. Fixed in DOSI. Solved. Problem solved. Error messages are not an issue. You will have instances where you're looking for a type class though, and you will literally get just I could not find an implicit. And the way to debug it is to sort of then look for an implicit for the next type down in your search, and next type down, and keep breaking it down. Compile times. Well, we're doing implicit search. Implicit search is one of the sources of compile times. So let's say we have some big data. That's my big data joke. It's quite big, right? Let's say the last field in that data is something that we don't know how to get a pure for. I haven't programmed an instance for a date. Now you can imagine that we're going to have to do a lot of work to break this into a giant sort of H list and work all the way down until we see, oh no, sorry, I can't do dates. So when we get large representations for these types, and then they fail very late in the implicit resolution, then we can get increased compile times. Now, this is probably unlikely. You probably won't have a case class like this in your code, but you might have some case classes like this. An outer has 3 middles, a middle has 3 inners, and an inner has 3 strings. So if you think about generating a pure for outer, we're going to have to go through 3 times 3 times 3 combinations of things to find that. And that will take a certain amount of time. Now, the way to mitigate that time is to declare, you can use this thing called cached implicit, where you can say, well, let's deal with the smallest data type first. We can solve that by looking at just the 3 fields, and we assign that to an implicit val. And then one of the things the Scala compiler will do is, if I'm then looking at middle, and it has to find instances of inner, if there's an implicit with exactly the right type, the Scala compiler will immediately choose that and not do any other search. So this makes this a lot faster. It makes it, we can sort of do things in 3 plus 3 plus 3 steps rather than multiplying. This is a good tip. Also, there's Miles's Y inductive implicits, which I haven't looked at all, so I don't know how much turning that option on will make this faster. It will make this faster. There you go. So you can also go and look at type level Scala and turn on that option. Okay, cool. So we've got to choose a winner. So I think the shapeless solution here is a lot more compact. It's a lot more compact and easier to understand. I mean, okay, some of this code is like very foreign if you sort of don't write it normally, but once you've got the idioms, it's actually very it's very idiomatic. It's very easy to follow the patterns. So the reason we're getting a good solution with Shapeless here is because of the nature of the problem and the nature of the tool. The tool is about looking at type structures and solving across the structure of types, and that's the kind of problem we've got. But one thing to bear in mind is that most of our solution, most of our code here is really just writing regular Scala code. The bit of magic that Shapeless provides, we don't actually see, right? So most of what we're doing is just writing regular code, and we'll see that in the next example as well. One of the larger points I want to make is, by using a type class, we managed to make both of these solutions better and simpler, or we managed to make both of these solutions general. Like with the macro, before we used the type class, we had a really limited solution. Once we introduced the type class, we could solve for any type. Same thing's true with Shapeless. So by using the tools that Scala gives us, we make our lives easier. I'll give you another example of that. Have any of you used MacWire? So MacWire's cool. It's dependency injection thing that uses macros. So let's say I have a database and some routing and a service that uses the database and the routing. I can write wire the service, and it will expand it into a constructor call. Now, the key thing about MacWire is, and this is a design decision of MacWire, it doesn't use implicits. It's looking these things up by you go from the wire macro, and it's looking in scope to find things of the right type. It seems just like implicit resolution. It should be easy, but there's this gigantic module of code in MacWire that does all of the looking up through the scope chain and looking at all your imports and finding things that have the right constructors and apply methods and stuff. It's very complicated, and they had to solve this problem themselves because they didn't want to use implicits because it deals with implicits differently. As I say, it's a design goal, but by just using implicits, we bypass this problem altogether. And I think that's a sort of an illustration of how we can make our metaprogramming easier by using the features of Scala. Let's have another look at an example here. So my second example is about validating data. There's a little library I've been putting together recently called Checklist. I've done a couple of talks about functional data validation. It's a bit of a hobby fascination of mine. And the idea is this is for runtime validation. So let's say, again, we have our case class. There are some properties in this case class where the types give us constraints, like we know the fields had to be certain types, but there are also properties of this case class that are not represented in this type, like we want the number of cherries to be a 0 or positive number. We don't want it to be negative. And we want the name to be a non-empty string. So we can deal with these in two ways. We can either use a library like refined to put them in the types, or we can write some validation. So this is roughly what the code in Checklist looks like. I've simplified it a bit for the slide, but what this does is build a rule that it's basically a function, and we can pass an ice cream in and it will give us a list of error messages. So we're saying, hey, look, this field should be a non-empty string, this field should be greater than or equal to 0. Now here's the thing. When we call the rule, the error messages we get back have the locations of the errors in them, because the primary goal of this is to give information to REST clients and say, hey, look, you gave us this JSON blob, these fields were wrong, these are precisely the fields you've got wrong, fix them. Right, so it's nice and helpful. So what we're doing is we're using the name of a field in our case class as a string. Okay. So this is the problem we try to solve here. We don't want to have to actually write the string as well as the accessor method. We want the metaprogramming to deal with that. So let's see how we do that with macros. With macros, what we're going to do is we're going to implement field as a macro, and we're going to take this accessor and we're going to generate a string literal and use the accessor as is. And I'm going to show you how that works, but I'm going to show you in the context of the library. So I want to describe a little bit about how the library works before we talk about the metaprogramming. So we're building a rule for an ice cream here, right? And it has a bunch of different properties on it. But the entire checklist library is made up of lots of smaller rules that we're combining together. It's a functional approach, right? We take small things, we build them into bigger things. So for example, this GTE0 here is a rule that checks an integer. And if we take that rule, so we say a rule is GTE, we apply it to a number, we get back an error message. Now notice here that this nil on the right is where the field name was previously. It's an empty list here, which means the entire data structure is incorrect. What I can do though is I can call this prefixed method on a rule to take the rule that doesn't give us field names and turn it into a rule that does give us field names. So it still does the same check, but if the rule fails, we get the field name on the result, and we can prefix and prefix and prefix and prefix. Okay? What we can also do is call this contramap method. For those of you who are not familiar with contramap, it's like map, but the other way around. So with a map, you start off with like an option of an A, and you map a function from A to B, and you get an option of a B. With the contramap, you start with a rule to check an integer, and you put a function from ice cream to integer, and you get back a rule that will check the ice cream. So the result of this is a rule which will take in an ice cream, whole ice cream, call cherries, get the number, pass that through this rule here, and then if there's an error message, prefix it. So we get back the result from our whole ice cream. Now, you can see where we're going with this. This is the string we need, and this is the accessor we need. So we've already got, without doing any metaprogramming, we have a library which does everything we need it to do. And now all we're going to do is take code that looks like this and turn it into basically, oh, I'm going to use this rule and this rule and this rule and bolt them all together. And there's some applicative thing going on here, but I'm just going to ignore that. So let's have a quick look at the code. Here's our macro, right? So it's a field method. This is our accessor. This is our subrule, and we're going to implement it in terms of this macro. Now, I'm breaking with tradition. I'm going to show you all the code. This is the code, all of it. So all we do, this block of code here looks up the name of the accessor. So it's assuming your accessor function is just a function to a field. And if you can't, if it's not, if you pass it some other function, something that's not syntactically correct, it will fail. So again, we can provide a nice error message, but it does mean that this only works in one situation. It just so happens, I think that's the situation we need. And the worst case is we can't use this macro, and we fall back on using prefix and contramap, right? So we can still write the code in other situations. So then all we do is we take that and we generate the code we need. So similar length to the Shapeless code from last time, and I think this is actually pretty easy to understand and pretty easy to pull apart, and it gives us the transformation that we need. So it's extremely short and simple, and that, I think, I would attribute to the nature of the problem we're trying to solve, which is a syntactic one. We're simply trying to look at a piece of code and pull out a name of a method as a string. And that's syntax. It's a very small problem. So the macro works well there. How do we solve this problem with Shapeless? Well, we can. You may think we can't, but we can. I'll give you a high-level overview of how this works. This is very powerful stuff. We can use this other thing from Shapeless called a label generic. So this will turn our ice cream into a type that has not only the types of the fields, but it also somehow tells us what they're called. And Mars alluded to this morning. The way we're doing this is using these things called literal types. So this field type here has got two type parameters on it. One of them is actually giving us the field name. So this is this is a symbol, right? You put a single quote, it's a symbol. It's a bit like a string. It's got different syntax. I'm not even sure why there are both types, but there are. So this is the type of the symbol name. It's a subtype of symbol, which is the type of all symbols. This is the type of just that one symbol. So you can say, well, I'm going to have name, I'm going to put it in a variable of type symbol, or you can put it in a variable of type name. So this syntax you can use as of recent Scala, let's say, because I can't remember the numbers. You can also, the classic example is the 42. So you can put 42 into a variable type int or a variable type 42. Still just an integer, it's just that we have a very specific type. Because we have a very specific type, we can look up type class instances based on that type. So we can actually, and Shapeless provides mechanisms for us to sort of convert from the value name to the type name and back again. So what we're doing with our rule is we're actually putting the symbols in here, and they get implicitly converted into a thing that has the right type. So then this is the code. So we have a type class we're looking for, which sort of does the plumbing. But again, we're looking at an H list, and we say we've got a name and we've got a value, and we're looking at and we have the generic case again to map. So I don't want to go into the details. Read my book. Was it time to book? 27 minutes, 58 seconds. Read my book if you want to understand this a bit more. But there you go. You can do it. But I'm going to say I think the macro solution is a lot easier to understand here. Again, because of the nature of the problem. So, I'm coming a little bit under time, actually. That's kind of interesting. Let's look back at what we covered. So there's two take-home points, really, here. One is macros are good for syntactic stuff, and Shapeless is good for structural stuff. So if you're choosing a mechanism to solve a problem, this is your first port of call, right? And then there's all these caveats about compile times and error messages and so on, and we've basically looked at the key issues. I've referenced the key issues in this talk. But the other big take-home point I really want to drive home is that in both situations, most of the complexity is about building a good library. So with the checklist example, we already have all the mechanisms to do everything we need without using macros and without using Shapeless. All those things are doing are just providing a nice syntax on the top. And if we use that as a foundation of building our libraries, it's going to make life a lot easier, especially when people say things like, well, you shouldn't be writing macros because Scala Reflect is going to be deprecated in Dotty, so you have to replace that with Scala Meta. Well, if your macro is only 20 lines long, it's not a problem. So This is the right kind of approach. The other thing is, remember, using things like implicits gives us a lot of power that we then get to use in our metaprogramming. So this stuff happens for free. We just expand into a call to implicitly, or expand into finding a type class instance, or we use a type class in Shapeless, and it'll solve all these problems. So the sort of the take home slide there is, we always want to use this stuff as a convenience, not as a solution, unless we're doing really crazy things. Okay, further reading. I've really talked very high level. I haven't gone into any detail about this stuff. This is where you look for the detail. Macros. I did a talk on macros. It's a talk for people who don't know anything about macros, and so that's probably a good place to start. Toma gave this great talk on using macros for validation. It goes into way more detail than I've done here, and he has a slightly different technique. And Chris Birchall's got a really good talk from Scala-italy earlier this year. This is actually an LSUG, a London Scala user group version of the talk, which has a slightly higher resolution version of the slides. As Shapeless, there's this book. You should get a copy of this book because it doesn't cost you anything, and you should read it, and your life will be better. This is the talk of the book, which is sort of the first. It's just 20 minutes. It's really sharp. It shows you one type class, all of the details that I skipped in this slide, going from beginning to generating the type class. And if you want a version of that talk that goes into way more detail and have someone who really knows what they're talking about and has actually built production libraries using Shapeless, Sam Halliday's workshop here, he talks about JSON serialization using Shapeless. So Spray JSON Shapeless, one of the type level libraries is his library that he talks about in here. Finally, my other point about most of your benefit here is going to be from writing good functional libraries. How do we write good functional libraries? Well, we do a lot of Scala training and things like this, and we have a lot of opinions on this. So this is my colleague Noel. He has this talk, 6 core principles for learning Scala. There's really about 4 core principles, I think, that are the really important ones. But that sort of just shows you the things that will help you build these libraries. And on the subject of validation, again, I've done 2 versions of the same talk with slightly different content that sort of work through going from nothing through to simply checking if something, true or false, is something valid, through to having an error message, through to making it monadic, through to applicatives and so on. The sort of progression of design. So that's stuff to go next to look at this stuff more. So oh God, I'm done so early. It's crazy. This took 40 minutes when I was practicing it. So thank you very much. Does anyone have any questions?